Welcome back to part 2. We're going to be continuing our discussion about collisions with another example. We're going to look at a maximally inelastic collision, sticky collision of two carts. So last time we looked at an elastic collision of two carts. Now we're going to go way the other direction. So, sticky. All right, so the same setup as the previous example. But now the carts are stuck together. So maybe they had sticky tack. Actually, I believe my carts have Velcro, which is what sticks them together. Therefore, each has final momentum P1 x final is equal to P2 x final. So they're moving together, they're going to have the same momentum at the end as one larger, more massive object. All right, so let's look at the final momentum. Final speed and final kinetic energy. Of the carts in terms of initial values. Once again, we are working only in X. Our system, both carts. Our surroundings. We have the earth, track, and air. Once again, neglecting friction and air resistance. All right, so now that we've got that set up, let's go into the momentum principle, which always holds. Final momentum's always equal to initial momentum. It's just the initial kinetic is not always equal to final kinetic. So P1 x final plus P2 x final is equal to P1 x initial. So 2P1 x final, because these have the same mass, they're going at the same speed, is equal to P1 x initial. So P1 x final is equal to 1/2 P1 x initial. Mass does not change. And therefore, V final is equal to 1/2 V initial. Okay, so now to go after translational kinetic energy. And we're still using the momentum principle. K1 final plus K2 final is equal to twice 1/2 mv final squared. K1 final plus K2 final is equal to 2 times 1/2 m 1/2 VI from up here, quantity squared, is equal to 1/4 mVI squared. So therefore, K1 final plus K2 final is equal to K1 initial divided by 2. All right, so now we know there was an internal energy change. What is it? So what is the change of internal energy? That is the question. Now we can bring the energy principle truly to play. K1 final plus K2 final plus E internal final is equal to K1 initial plus E internal initial. E internal final minus E internal initial is equal to K1 initial minus K1 final plus K2 final. And so delta E internal is equal to K1 initial minus K1 initial over 2 using our previous result. And therefore, the change in internal energy is equal to K1 initial divided by 2. So the final kinetic energy being half the original implies half has been converted and sort of dissipated into increasing the internal energy of the carts. Now, something that is important to note. We needed both principles. To fully analyze this situation. So I told you, there are 3 main principles that we learn in Physics 1, momentum principle, energy principle, and angular momentum principle. So this is bringing 2 of those fundamental principles together. Angular momentum is in the next chapter, and yes, we will bring it to play with momentum and energy. All right, so moving forward. Head-on collisions between unequal masses. Let's go back to the Kuiper Belt. And play with balls in space. No gravity, no friction, way fun. So, Let me write space more neatly, slightly more neatly. All right, what would happen if you threw a marble at a stationary bowling ball? So you're in space, so you're wearing a spacesuit. Costs more than your prom dress, more than my graduation robes. That's what a spacesuit looks like. And you throw a marble, there it is, at a big old bowling ball. Because why wouldn't you bring those things with you to space? That's what I thought. So you throw it there, now what happens? So the marble bounces back with essentially very little change in speed. And the bowling ball moves just a little. Okay, so that's conceptually what happens. Now let's do this explicitly. So a marble traveling in positive x, it's got mass m, hits, it'll have momentum I, hits a stationary bowling ball, mass m, head on. After the collision, let's find p, the speed, and the kinetic energy of each object. All right, so first, we're going to assume if it bounces back with about the same speed, assume elastic and little change in speed of marble. So think all the way back to the early days of the chapters in Physics 1. So our system is the marble and the bowling ball. Our surroundings is nothing of interest. We are in space after all. It's basically a whole lot of nothing out there. Okay, so we've got our marble, P, with initial going towards the bowling ball. And then we have, that's the initial. And then we've got our marble going away from the bowling ball at the end, and P1 final is equal to minus P2 final, and we don't know P2 final for the bowling ball. So that's our setup. But we do know the momentum principle quite well. So P1 final plus P2 final is equal to P1 initial plus P2 initial. And based on our assumptions, P1 final is approximately minus P1 initial. So therefore, minus P1 initial plus P2 final is equal to P1 initial. So P2 final is equal to twice that of P1 initial. So this implies the final momentum of the bowling ball is 2 times the initial of the marble. So remember, speed is scalar and momentum is vector. And it contains the direction change. Okay, let's go after the final speed of the bowling ball. So, V2 final is approximately P2 final over M is equal to 2 P1 initial over M is equal to 2 MV1 initial over M is equal to 2 little m over big M times V1 initial. Okay, so something to note, this is a very small speed. So the mass of a marble is approximately 5 grams. The mass of a bowling ball is approximately 7.3 kilograms. So you have 0.005 divided by 7.3. This is very small. That momentum is basically tied up in the mass. So, if the marble has a speed of 15 meters per second, then you have 2 times 0.005 divided by 7.3 times 15 meters per second is equal to 0.02 meters per second, which is very small. Okay, so now let's go after the kinetic energies. So K2 final is equal to 2 times P1 initial squared over 2m. K1 final is equal to P1 squared initial over 2 little m. And once again, we can see how mass is going to scale things. So the mass of the bowling ball is much greater, implying a smaller k. So K bowling ball final is equal to 0.0015 joules, and K marble final is equal to 0.563 joules. So just a quick note, as you've probably already noticed, the kinetic energy of the bowling ball is very small, but not zero. And this implies marble did lose some speed. But we know macroscopic collisions are never fully elastic, but for all intents and purposes, this was good enough. Our assumption was an approximation. But what you can see from these examples is that using the momentum principle and the energy principle and a fair bit of algebra, you can go after several collision unknowns. All right, so this wraps up part 2 of Wednesday's lecture.